Hello everyone, my name is Sara Takhim, and in today's module, we will be looking at proof by induction, specifically weak induction. Now, before we begin, let's ask ourselves some key questions. What is a proof by induction? Now, before we begin, I want you to all think about something with me. Say we have a stack of dominoes, and I flick the first one over. The rest of the dominoes all have to come down too. A proof by induction, or PBI for short, is similar to our domino visualization. It is a mathematical proof technique used to prove a statement, P of n, which holds true. And we do this by showing that two different cases have to hold true. Now, how do we create a proof by induction? In order to create an accurate PBI, we first need to define our claim. What is our P of n? Next, we need to state and prove our first case, the base case. We must show that the base case holds true without assuming any prior knowledge of other possible cases. Now we can think of the next part as a ladder. When you think of induction, one of the best analogies that I tend to think about is the ladder. When you climb up the ladder, you have to step on the lower step and need to go up from the lower step. After we climb up the several steps, we can go further by assuming that the step that you are stepping on exists. Now, we have to state our inductive hypothesis. This will lead us to our second case, the inductive step. The inductive step proves that if the hypothesis holds true for any case where n equals k, then it must also hold true for n equals k plus 1. The base case and inductive case establishes the validity of the claim holding true, and you are finished with your proof. Now, in our problem, we will be proving that 9 to the n minus 1 is divisible by 8 for all n greater than 0. First, let's define our P of n. We can say that P of n is equal to 9 to the n minus 1. Next, we can start our proof by stating our base case, n equals 1. When n equals 1, we see that n to the first power minus 1 is 8. Additionally, we know that 8 modulo 8 is 0. Therefore, when n equals 1, the index is divisible by 8. We have proven our base case to be true for when n equals 1. Next, we can state our inductive hypothesis. We can assume true for n equals k, n to the k minus 1 is equal to 8x, x in the set of integers. Since the formula must be divisible by 8, it can also be a multiple of 8. Now, we must prove true for when n equals k plus 1. By the rules of exponentials, we can say that n to the k plus 1 minus 1 equals n to the k times n to the first power minus 1. Because n to the first power equals 9, we can simplify our statement to n times n to the k minus 1. From our inductive hypothesis, we know that n to the k minus 1 equals 8x. So we can also say that n to the k equals 8x plus 1 when we subtract over the 1 to the other side. Going back to n to the k minus 1 equals 8x, we can now substitute in our new value of n to the k. Now we have n times 8x plus 1 minus 1. We can simplify this to 8 times nx plus 9 minus 1, because we know that whatever we are solving for must be a multiple of 8. If we do some more simplification, we can see that 8 times 9x plus 9 minus 1 equals 8 times 9x plus 8. Now we can include the plus 8 inside of the parentheses. Now the equation will become 8 times 9x plus 1. We know that this formula is a multiple of 8, and inversely, it is also divisible by 8. Now, we have formally proven that our claim P of n holds true. As P of n is true for when n equals 1, our base case, it is also true for when n equals k. And we have shown P of n to be true for n equals k plus 1. We know that P of k implies P of k plus 1. Therefore, our claim P of n is true for all n greater than 0. We have finished the proof. So, when you are finished with your proof, you end by stating QED. Thank you all for listening to my lecture on proof by induction. I hope you enjoyed the video. Goodbye.